Okay, so we're stepping through some of the predictions of QED today, and I want to start off with something that has to do with infrared divergences. So I titled this Soft Radiation or Infrared Divergences. Okay, so infrared, just a reminder, of course, is low energy. So at low energies, we're going to find some divergences also. And actually, we've been dealing with one, and it's the thing I've been hiding from you. I told you last time I hid something from you. I'll unhide it today. But if we're doing these set of diagrams, plus ... there's something fishy goes on in the vertex direction. Okay, and you can see it. Let's just write it out. We have minus IE gamma mu, and I'm going to write it in using the scalars rather than vectors, just because it's easier to show you. So it's integral d4k 2 pi to the fourth, and you get minus IE 2p plus k mu minus I over k squared plus I epsilon I over p minus k squared minus m squared I over p prime minus k squared minus m squared, and then another factor of 2p prime plus k. Actually, I have a couple of those. So this is also, let's make that first one lambda, this lambda, and then sitting in the center there's also it's p plus p prime plus k. Plus 2k. Okay, and I can do the labeling. It's p prime, k going like that. It's actually what I ended up writing out. Okay, so pretty much like that. And there's a minus IE missing if I'm trying to be precise, but I'm not really that interested in being precise. I'm really interested in following the factors. But if anyone wants to ask anything about it, I'm happy to do it. Okay, so infrared means low energies, so when k gets very small. Okay, so all the stuff in the numerators, the k getting small doesn't do any damage. But there's a 1 over k squared there, and there's k's there. So let's just look at that. When we're on shell, so these external states are on shell, we have p minus k squared minus m squared is p squared minus 2p dot k minus k squared minus m squared, and p squared is m squared when you're on shell. So at low k's, this goes like, well, it's minus 2p dot k is the leading one, and then the k squared is small compared to that. So, at very low energies, I can drop k squared compared to p dot k. Fair enough? And so the gamma mu then has things in it, has integral d4k. There's a 1 over k squared from the photon propagator. There's a 1 over p dot k and a 1 over p prime dot k times stuff, which is, the rest of the stuff is well behaved. Okay. So for Jessica, we're talking about infrared divergences down at low energies. Okay. And the feature that you see out of this is that this goes like then d. This is going to drive me crazy. d4k over k to the fourth, which is log divergent at low energy. So that goes, if I just treat that naively, it goes to infinity. Okay. Now, this is, if you recall our philosophy on renormalization and divergences, this is very different from the renormalization divergences. Okay? The renormalization divergences come from unknown physics at high energies, and maybe they're there, maybe they're not, but we absorb them into coupling constants because they're very low energy, I mean they're very short distance, and so everything short distance has a parameter, and etc. That's the mantra that we do there. This is not, it can't go into renormalization. This is very long distance stuff. This is the longest of distances. So it's very different. So here's how we can imagine analyzing it. Let's temporarily take the photon and give it an effective mass. So instead of using 1 over k squared, we give it a small, tiny photon mass. And at the end of the calculation, we'll try and setting that to 0. Okay. Then here's what you end up with. So let's, you grind away. D sigma d omega is d sigma d omega 0, which is the piece without the radiative corrections. 1 minus, it's 2 alpha over pi log m over lambda times some function of q. Okay, that's what you get, and this is that infrared divergence there. If I just let lambda go to 0, this blows up. Okay, so I've regularized it, and f of q, just f of q squared starts like it's a minus a third q squared over m squared for small q squared. And at high q squared, it goes like log. Just like that. That's not relevant for what we're doing here. The first piece is relevant. The fact that vanishes, that's important. It does not screw up charge renormalization. Remember, if that had gone like a constant, this would have been a bad news, because you would have had a mass-dependent charge renormalization, because that's how we did charge renormalization. So this is with the renormalized charge. Okay, so that doesn't happen. Okay, but we still are faced with that divergence, and the resolution is soft radiation. Okay. There's another divergence in the following process. Here's a process where we do the same initial states and final states, except we allow for a photon of momentum k coming out there. Okay. So the matrix element of this, the matrix element of this looks like, I'm being a little schematic here, it looks like the basic matrix element, M0, the part from there. Then there's a propagator, 1 over p prime minus k squared minus m squared from the propagator piece, and upstairs there's an extra coupling 2p prime minus k. If this is polarization lambda, that's polarization, that's lambda. Okay, so that's basically the vertex. This vertex is slightly different because the q squared is modified by k, but in the limit that k is small, there's no problem there. But then there's a divergence here too. You get d sigma, let's just imagine doing d sigma d omega. We have a bunch of stuff. There's an integral over the phase space d3k over 2 pi cubed 1 over 2 omega k, lots of stuff, m squared. And so m goes like 1 over, okay, actually I need to say that. This piece here, by the same calculation we did above, looks like 2p dot k when we're, or 2p in this case, p prime, when we're at very low momentum, just same calculation. So the matrix element goes like 1 over k. Omega is k. So this thing looks like it's d3k over k cubed. And you can just see by looking at it that this momentum k is not constrained by overall energy momentum conservation. It can be any momentum you want, so in fact this integral has to get done. And so this goes to infinity also. Okay. So this is bremsstrahlung, which I always have trouble spelling. That's beam radiation, basically soft radiation from some process. And if you do the calculation, you get d sigma d omega for this radiation soft is d sigma d omega 0. It's 2 alpha over pi log. Well, let's cut it off at some maximum and k minimum. K maximum is just I have this integral to do, and there's some place where in fact this approximation of this being 1 over k fails. That's k maximum. K maximum is pretty irrelevant for what we're about to do. But then comes f of q squared, and it's the same one. And that's a bit of a miracle, but it always works. And now we notice the fact that up above there, this fortunately came with a minus sign. It was getting smaller as lambda goes towards 0. So it's not getting bigger. This is actually starting at 1 and going down, which fortunately, again, that minus sign is a bit of a miracle, but it always works. If you add these two, the infrared effects can cancel and add up to some finite thing. So the sum of these is well defined. Okay. So what we imagine doing is we say, let's take d sigma d omega for the scattering, the original scattering, and we add d sigma d omega for the radiated one, radiation, with k less than some delta E. So basically, what you're doing then is you're taking K max as delta E, and we're going to take K min to be the mass of the photon. Actually, you do it really more carefully when you're really professionally doing it. This is d sigma d omega 0. They're all proportional to that. 1 minus, it's 2 alpha over pi, this f of q squared. But then we get log m over delta E plus some constant. And to get the constant right, you have to really do it really carefully. Okay, so I'm certainly not doing that. Turns out to be a 11 over 24. You know, how many times do you see 11 over 24 in a physics calculation? So but that's what you get. Okay. So this is now a perfectly well-defined number, and it's basically what you would measure experimentally. There's always some delta E, such that if you radiate a very soft photon, that you can't see that. So in some experiment, there's some energy resolution. So you're sitting there, and if you radiate a photon that carries 1/1,000,000th of an electron volt, you never see that in your experiment. So there's always some cutoff like that. And you can you then have a nice finite prediction for your cross-section. It seems a little funny. Your prediction depends on your experimental resolution, but I have seen experiments where they can vary this resolution over some range. You have a detector, and you can say, let me accept photons of this energy, this energy, this energy, but of course you can't go down forever. But you can actually see the effect of this piece here. You can see the delta E effect of including different amounts of soft radiation. But then you have to stop at some stage, and you can never get down to a place where this thing ends up giving you trouble. It's a funny little process. It's actually, you might worry that you could make this term so big. Remember that f of q squared at high energy goes like log q squared, so that could be a big number. Alpha is a small number, but still, maybe you could get it to 2 big logs, and you can make that one. And the answer is that no one's done it, but there is actually a formalism for summing these effects if you're trying to be fancy. So this actually is the first term of a series of corrections that are all well behaved. It actually turns into some exponential, so it's e to the minus something instead of, you'll never go through 0. Okay? It just gets smaller. Okay, so that's in scattering soft radiation. Okay, now that we have that, I have to correct the hidden piece of the lamp shift. If you remember, I said I hid something. And here's what I hid. We were looking at that same diagram and said part of that goes into the lamp shift. And the way we did it is I had this vertex here, 1 over q squared, and that vertex had a function f1 of q squared, which I said was 1 plus a q squared over m squared. And that combined with the 1 over q squared there, the matrix element then had a 1 over q squared piece plus a constant piece coming from the q squared canceling the 1 over q squared. And this gave me my delta of x, which is the lamp shift. Okay. Well, But now all of a sudden I've told you that A actually has an infrared divergence in it. So A, which I didn't show you before, A is minus 2 alpha over pi, 2/3 alpha over pi, log m squared over lambda squared. Okay? Okay. So what's going on there? Now, this case, I can't cancel it with bremsstrahlung. Okay? So there's no radiation. No soft radiation. Okay, so it looks like I'm in trouble. Here I can't use this trick above canceling it by radiation diagrams, but I'm not. Of course. The trick here is that I'm off shell. I'm not on shell. So remember, the divergences that we got before came from taking p squared minus let's make it p minus k squared minus m squared going like 2p dot k. And this again was p squared minus 2p dot k minus plus k squared minus m squared, and we set p squared equals to m squared. But here we're in a bound state. Here, the energy is the mass minus the binding energy. And so this then p squared minus 2p dot k minus m squared goes in the soft region there. It's basically p0 squared here, which is m minus b squared, goes into 2mb, which then saves the day. This doesn't blow up. As k goes to 0. So the effective thing that you really get then is you end up getting A is roughly minus 2 alpha over 3 pi log m squared over mb which is nice and finite, and in fact the reason why the vertex direction was so much bigger was this m over b is a big number. The binding energy is of order eV. The mass of the electron is a half an MeV, so it's a relatively big number, but that's why the vertex direction was so much bigger. Okay, so these soft effects take a lot of work. They're not real easy, but they always work out in somewhat miraculous ways. Soft divergences are never really divergences if you think about them clearly enough. Okay. Anybody have questions on that? Okay, last of the predictions. I want to go a bit through G minus 2. Okay, and I'm not sure if you've all seen the way to show that the G factor for the electron is 2. So I'm going to quickly do that. In fact, I'll do it a couple ways. It's also needed to show how to do the calculation. I'm not going to do the full calculation for you, but I am going to hand out the full answer. the full calculation to you once we get there. Okay, so here's how the easiest way I know to show it. Let's start with the Dirac equation. We have I d slash minus m psi is equal to 0. Okay, but since that's equal to 0, if I multiply it by I d slash plus m, it's still equal to 0. Okay, so that's a marvel of modern mathematics. And if you look at that, that's minus d slash minus m squared. Okay, the cross terms cancel, of course, psi. Okay. Now, you'd be tempted I've told you that if you have any vector, any vector slash equals vector squared, but it's not true for if that vector is d. So the theorem, if vector is not d. Okay, but d slash is not equal to d squared. And the basic reason is that d contains two pieces that don't commute. Okay, and so for here's what you have. If you have d nu, there's two pieces that don't commute in there. One's the derivative, and the other is the minus IEA. So, well, let's just be a little pedantic here. It's d mu minus IE a mu d nu minus IE a nu. Okay? Well, you know, if the derivatives that you have here were not acting on the a's, then the derivatives would commute, the a's would commute, everything commutes. But the piece that doesn't is when the derivative acts on the a. So there's a derivative mu on a nu, and then in the reversed order there's a derivative nu on a mu. So the non-commuting piece of this is minus I E F mu nu. Okay. So if I have gamma mu, gamma nu, d mu, d nu, okay, if we want to work that out, what we do is we write it the following way. You write it as 1/2 the anticommutator of gamma mu, gamma nu, plus the commutator of gamma mu, gamma nu. Okay. The first term is the one ordering plus the reversed ordering. This one is the first ordering minus the other. So this this is an identity. This guy, of course, the first one is 2g mu nu. That's the piece you normally pick up. This guy is antisymmetric. That's minus sigma mu nu. And since so the first term gives you the d squared piece, is then d squared, the usual d squared, and the second term is minus, actually I need an I right there, e over 2 sigma mu nu f mu nu. Okay, so that's what we have. So our equation then is d squared minus e over 2 sigma mu nu f mu nu minus m squared psi is equal to 0. So that's just a fancy version of the Dirac equation. I've just multiplied through by a particular thing. Okay, now let's do the following. Let's take a magnetic field. I'll put it in the z direction, so it will take A1 is minus a half by, A2 is 1/2 bx. So then F12 is d1 A2 minus d2 A1 is then b. That's the field in the z direction. That's our normal definition of it. And then d squared is the following. D squared by itself, let's just look, I'm just going to look at d sub I, that's where the action is d I squared minus IE d I AI plus AI DI plus a squared. Okay, the a squared piece is of order b squared. We're not interested in it. But again here, you've got some things that don't quite commute. The derivatives. If I write this with the derivative on the other side, then there's a piece, to get it there, there's a piece where the derivative acts on AI, and well, actually, I forget this. The commuting doesn't make much difference here, actually, if you think about it. So this is, yes, so for these, actually, yes, that's right. For these, this first term here, actually, is the same as AI DI for this particular ones, because A1 doesn't involve X1, A2 doesn't involve X2. Okay, so the commuting isn't relevant. But if you go back and you plug in here, you get di squared minus, it's 2IE over 2 bx d by dy minus y d by dx. Okay, so the d by dx piece comes with a y, and the d by dy piece comes with an x. Okay, so this is then, is di squared minus EB times R cross P. Okay, if I look at in general, it's EB dot R cross P. So there's a piece here which goes like the angular momentum. On the other side, there's going to be a piece that goes like the spin from there, and here's how you get that guy. If I look at sigma ij, well, I won't calculate it. If it's epsilon ijk, sigma k, 0, which is epsilon ijk times 2 times the spin operator, kth component. Okay, so sigma 12 f12 plus sigma 21 f21 ends up summing into 4f dot b. And overall, this calculation that we've gone through, we get d0 squared plus m squared minus del squared minus eb dot l plus 2f vector on psi is equal to 0. Okay, so this is the g is equal to 2 calculation. That's the 2 that sits right there. It's L plus 2s is the 2 of the g factor. Okay, so it's really just playing with the Dirac equation. Okay. I have to, as a prep for what I want to show you how the calculation goes, I have to do something that's actually turns out to be equivalent. So let me do the Gordon decomposition. Okay, and again, I guess given time, I'm not going to completely derive it. It's not that hard to derive. But basically, if you're looking at this coupling here, the electron-electron photon coupling, we would normally write that as u bar of p prime gamma mu u of p. Okay, and then there's a way to massage that, and it turns into, and basically the trick is at appropriate times you put p slash minus m there, or p prime slash minus over m there. Okay, so because p slash equals m when acting on the spinner, and p prime slash equals m when acting on that guy, and you just do it in the right places, and then you've got two gamma matrices there, and two gamma matrices can be reduced to 0 gamma matrices, or the piece left over is sigma. So here's the identity: u bar of p prime. You get p plus p prime mu over 2m plus I sigma mu nu q nu over 2m okay. So, and you can sort of see how you do it by you put a p gamma mu p slash here, there's a commutator and an anti-commutator. The commutator gives you the p mu, the anti-commutator gives you sigma mu nu times the q, the p that's in q. Okay. So this is the Gordon identity. What you see here, this is actually interesting for a couple reasons. This guy is the convective piece. It's called convective. That's just like a scalar. You remember, if we had written this vertex, the same vertex out for a scalar, we would have written p plus p prime. And aside from a normalization factor, that's the same thing. This is the piece that gives you the L, because just a scalar would have an L dot B coupling. You get the L piece from there. The sigma mu nu piece, by the argument that I gave up above, gives the S piece. Okay, and so the point is that looking at the factor in front of the sigma mu nu q nu, you can get out the magnetic moment piece. Okay, that's this. And then the part that goes into the calculation, so to set up the calculation, we recall we wrote this vertex out plus the original one, and our names were, we wrote it as minus IE, U bar. I want gamma mu F1 of Q squared minus I, or plus I, sigma mu nu over 2m Q nu F2 of Q squared. And I argued that was a general decomposition because of the conservation of the current. I now apply Gordon decomposition. This turns into minus IE U bar F1 of Q squared gamma mu. No, sorry, this is now P plus P prime over 2m. And I get plus I sigma mu nu over 2m Q nu F1 of Q squared plus F2 of Q squared. Okay. We also showed that by charge renormalization and the word identity, that F1 of 0 was just 1. That says that the overall charge that is here is the renormalized charge. And picking out the S part here, we see that the magnetic moment is mu is E over 2m 1 plus F2 of 0, which, since the 1 corresponds to G equals to 2, implies that G minus 2 is F2 of 0. Okay. Okay, so that's the prep for the calculation. Okay. So all we really have to do then is to do the calculation. We do this diagram, and pick out F2 Q squared is equal to 0. Okay. The answer when we work it out is F2 of Q squared is alpha over 2 pi integral 0 to 1 dx me squared over me squared minus Q squared 1 minus x times x, which goes as Q squared goes to 0, alpha over 2 pi. Okay, so that's the famous calculation there. Here is the calculation. So for all of you in class, I have 2 handouts for you. One is, I have prepped this and I've taught it before, but given where we are in the course, I think it's not worth it to spend a half a day doing the whole calculation. And the second one is the summary of where we are in G minus 2 by the guy who's devoted his career to this. Tom Kinoshita has made it his full career. From start to finish, he's calculated G minus 2 at higher and higher precision. It's not for me, but it's quite the career accomplishment. If you look at the description there, they're up to 4 loops. So this first piece was calculated by Schwinger. That was a triumph of its time. But now the G minus 2 factor, so it's actually 1/2 G minus 2, is 1.1, no, actually it's a comma here, 1,159,652,175.7. Love the times 10 to the minus 12. And I dare you to find any other calculation that's actually, to be fair, this is actually the experiment. The experiment is that with an uncertainty of 8.5 in the last digit. So this means that this 5.7 plus or minus 8.5. Okay. Actually, no, that is the prediction. I'm sorry, back off. That's the theory. Okay. Most of that uncertainty comes from just not knowing alpha to that high precision. Basically, this is so precise that if you don't know alpha to enough digits, you can't predict this any better. So that's basically the biggest uncertainty there. And if I take experiment minus theory is 12.6 times 10 to the minus 12. Okay, actually I need to put my uncertainty on there. It's 12.6 plus 9.5 is so the theory uncertainty is still the largest. You can see taking the difference, this 8.5 went to 9.5, so the experimental one is of order unity. Is smaller than the theory one, and the theory one comes from alpha, so that's in some sense experiment too. But within reasonable expectation, that's an amazing agreement. Okay, the muon one is not as well known. So there's the good news. The bad news is the muon one. The muon one is less clear. The muon mass is bigger, and it's more sensitive to things that are hard to calculate. So it's more sensitive to quarks, which are harder to calculate. The diagram that causes the most trouble present is this one, where you take 2 photons coming there. You have a quark loop. You have quarks there. And that's not really easy to calculate at low energies. It's called light by light scattering is the phrase, because it's 2 photons goes to 2 photons through a quark loop. You can calculate the electron loop well, but not the quark loop. And here, the difference, the muon's anomaly experiment minus the muon's anomaly theory is 209 with an uncertainty of 97 times 10 to the minus 11. Okay? And so, it's there a little bit over 2 sigma. You just don't know what to make of it. 2 sigma is not so wild that you go running off and claiming a discovery, but it's a little bit uncomfortable. Okay? People who love supersymmetry will adjust supersymmetry to make the correction just happen to be about 209 to make it come into agreement. Okay. So, anybody want to chat about any of those things? Okay. If not, here's what I'd like to do next. What I'd like to do is I'd like to take QED. So we're finished now with our discussion of what the active stuff in QED is. There's more to say, but that's where I'm going to stop. Take QED and use it to write out YangMills theory, like QCD or the standard model. So our goal now is YangMills. Okay, and the phrase YangMills refers to a gauge theory where the symmetry, the gauge symmetry, is SUN, n being 2, 3, 4, etc. Okay, so all these get called YangMills. So QED, if you remember, had the gauge symmetry that the field in QED goes to e to the minus I. Just take a phase, alpha of x, psi, and the photon field goes to a mu plus 1 over e d mu alpha. Okay, and when I did it first time, I put an e up here, and there was no e here, but it's just a relative factor. Alpha is arbitrary. So you could do it this way. Okay, this is in group theory language, it's the U1, the unitary 1-by-1 matrix is just a phase, is represented by just a phase. So this is a U1 gauge theory. Okay, so now I need to tell you about SUN. Okay, and I know some reasonable fraction of this class is in Gala, which is a group theory class. And I'm not going to reproduce all of that, of course. I'm going to just do some practical group theory. Okay. Which means I'm going to introduce the SUN transformations to begin with. Okay. And let's start with 2. N equals to 2. Let's imagine that I have 2 fields. 2 fermion fields, for example. Psi is psi 1 and psi 2. Okay. Now, what invariances would be possible with 2 objects? Well, clearly the type of thing that would preserve quantum mechanics is unitary transformations on these 2 guys. So I could make psi prime is some unitary transformation of those 2 guys. Okay. So this is a 2-by-2 unitary. Okay. 2-by-2 unitary can be written, you can always write a unitary matrix as e to the minus I times the Hermitian matrix. This is there's a math theorem for you in general. So you can write U is e to the I times the 2-by-2 Hermitian matrix. And 2-by-2 Hermitian matrices can be represented in terms of an identity matrix. So alpha, let's call it alpha 0 times the unit matrix, and then the 2-by-2 non-trivial Hermitian matrices are the Pauling matrices, which I will call tau. So tau here is the Pauling matrices. So, but just to keep we want to keep spin out of the game. It's just, these are just the 2 by 2 Pauli matrices. Okay. So this guy is still a U1 transformation. That's just an overall phase of the whole field. It's just like up above. The second piece here is the SU2 transformation. Okay. The SU2 stands for unitary 2 by 2 with determinant equals to 1. And you show that the determinant of any matrix is e to the I times the trace log of the matrix, and these guys, trace log u. There's another math identity which I won't prove for you. This then is alpha dot tau. These are traceless. Okay, we don't really need to know that, but that's how the name comes about. Okay. So here's our potential invariant. Okay. Now, when is that an invariant? Well, it's if we have a term in the Lagrangian that goes along like, so there's a psi bar O psi. Under this transformation, this goes into psi bar U dagger O U psi. So this is an invariant if O is equal to 1, the unit matrix, the 2 by 2 unit matrix. Okay. So, for example, if I chose O to be I del slash minus M, and I choose M to be the same for each of them, so it's proportional to the unit matrix, that will be invariant. Yeah, so I'm going to come up with another one that's an invariant also. But certainly, if I just say that if O is 1, this is certainly an invariant, right? You won't deny that. Okay? More interesting is some things, well, let me go through one that's not an invariant for the moment. Let's look at a particular one at psi bar tau I psi. Okay. So now there's a tau matrix in there. This goes to psi bar U dagger, that turns into U dagger tau I U psi. And if you look at this, that guy it's a 2 by 2 matrix. It's Hermitian, right? It's because it's U dagger U, and it's also traceless. Okay, so the combination 2 by 2 Hermitian traceless uniquely tells you that it's proportional to some tau j. It's some other tau matrix. So this guy is written then as psi bar tau j psi rij. So this ends up transforming not as an invariant, but as sort of as a vector. So psi bar tau I psi goes to psi bar prime tau I psi, which is rij psi bar tau j psi. Okay, and actually, you can actually figure out what R is. So we've said U dagger tau I U is this Rij tau j. Since these are Pauli matrices, I can take the trace on both sides. So let me take the trace over here, multiply by tau j, and take the trace, and multiply by tau j. This thing trace is just 2. And so Rij is 1/2 trace U dagger tau I U tau j. So there's what it is. So given a U, I can convert that. Okay. The thing I won't do, but which is true, is this is a rotation matrix. So this rotates like a vector does in tree space. And this is the origin of, and this isn't that relevant for our discussion of YangMills, but that's what it's. This is a element of the group O3. These are elements of the group SU2. And so there's this local isomorphism between SU2 and O3, but it's not an identity, because if I took U to be -1, then R is +1. So there's a sort of a 2-to-1 mapping here. As I go around SU2, do all these transformations, there's one of those transformations where that U turns into a -1, and R is +1. So there's a 2-to-1 mapping. That's not relevant for our stuff, but that's what it is. Okay? But what I do need to use that for is I need to make invariants with interactions, because this is how we're going to do it when we do YangMills, which is clearly going to happen next time. So let's look for invariants that way. Okay, so let's imagine we couple this vector here, psi bar tau I psi, to some other field, which I'm going to call pi here, because this is a standard one, where those are actually the 3 pion fields that you find in QCD. Okay, we'd like to make that an invariant. And how can we do that? Well, you can make it an invariant by making pi transform like a vector also. Okay, the algebra of that is, I showed you, or I partially showed you, that this transforms like a vector. You make that transform like a vector, and it works. But here's our practical shortcut to this. I'm going to write this as psi bar prime tau dot pi psi, right? So that's what I've done. And we can see a simpler notation than making that using that as a O3 vector by doing the following. If pi prime, so I take pi into pi prime such that tau dot pi prime is u tau dot pi u minus 1, or u dagger. Okay, so let's just assume that I'm going to do that. Okay, then we have L goes to psi bar prime. No, well psi prime is u dagger. This is then u tau dot pi u dagger, and psi had turned into u. Okay. So if I choose pi prime that way, then these guys cancel, those guys cancel, and this is psi bar tau dot pi psi. Okay. This looks a little formal, but it's again not that hard to do, to actually write out what that rotation is. The explicit form of this is the following. If I want to pick out what pi prime is, so this is tau dot pi prime, let's multiply, take tau j, well, actually let's do tau I times tau dot pi prime. Okay, and then take the trace. Okay, so this is tau I, tau j. That's a tau. There's the tau and the pi's over there. Tau pi. Okay, that's 2 pi prime I. Okay, because the trace picks out the tau that's tau I. And over on the other side we have, this is trace of u, well, tau I, u, tau j, u dagger, pi j. But if you remember, that's what I called Rij before. That's, I said, was a rotation vector. So this is pi prime I is Rij pi j. So it does transform like a vector also. Okay. So what I will want to do is use this type of transformation here when I'm constructing YangMills to simplify my life, because the algebra of doing that is painful. Okay, and I guess I'm going to stop my practical gauge theory there. We'll come back. I'll just repeat this thing as a summary, taking SU2, which we just did, to SUN, and we'll go from there to YangMills. Okay. And that's not going to take the whole class next time. It's just going to take the starting part, and then we'll transition from that into discussion of path integrals. Okay, good. See you next time.